Welcome back to The Explainer. Today, we're taking a massive leap forward in our line modeling series. We are translating the physical realities of transmission lines into practical, workable, mathematical models. I mean, if you've ever wondered how engineers take hundreds of kilometers of high-voltage wire and just tame it onto a single sheet of paper or into a computer program, well, you're in exactly the right place.
Okay, let's jump right in. Last time, we established that transmission lines aren't just simple wires. They're actually distributed systems. Remember that flat surge impedance loading voltage profile we looked at? Yeah, a voltage change at one end doesn't just instantly teleport to the other. It actually travels as a wave over time, moving at nearly the speed of light. That is the core reason why long lines behave completely differently from a simple lumped circuit you'd have on your workbench.
But hey, here's the great news. You rarely ever need to solve the full, complex wave equation for practical day-to-day power calculations. Instead, we rely on three simplified models based entirely on physical distance. These three, short lines under 80 kilometers, medium lines up to 250 kilometers, and long lines over 250, they cover essentially every transmission line you will ever design or analyze. Let's look at exactly how we model each one.
Starting with the short lines under 80 kilometers, notice how beautifully simple this circuit becomes. At these shorter distances, the line's shunt capacitance, which is that electrical field effect between the conductor and the ground, is so incredibly tiny we can just ignore it entirely. We simply model the whole line as a single series impedance from end to end. It's literally just the resistance from the conductor material plus the inductive reactance from the magnetic field. That's it. Your voltage drop and power transfer calculations reduce to basic foundational series circuit algebra.
Now, as we scale up to medium lines, so between 80 and 250 kilometers, we cross a bit of a threshold. The line is now long enough that we absolutely cannot ignore that shunt capacitance anymore, because the line charging currents are getting significant. But we still don't need the full distributed wave model. Instead, we use the nominal-pi circuit. We take the line's total series impedance, lump it right in the center, and then split its total shunt capacitance into two equal halves. We anchor one half at the sending end and the other at the receiving end. This creates a shape just like the Greek letter pi, and man, this is the absolute workhorse model for most of your real-world sub-transmission studies. So, what happens when we go even further? For long lines exceeding 250 kilometers, especially as you approach 300 and beyond, even that trusty nominal pi model loses its accuracy. The physical distance is just so vast that those distributed wave effects become impossible to ignore. To handle this, we don't throw away the pi shape, we upgrade it. We apply mathematical hyperbolic correction factors, specifically using the sinh and cosh functions of the line's propagation constant, to rigorously adjust the equivalent series impedance and shunt admittance. The result is what we call the equivalent pi model.
This comparison brilliantly illustrates the core difference between the two approaches. Nominal pi is our lumped parameter workhorse, perfect for those medium routes where we can just split the capacitance and call it a day. The equivalent pi model, on the other hand, mathematically corrects for true wave behavior. Structurally, it looks completely identical on a diagram, sure, but the actual component values have been heavily modified by those hyperbolic functions to account for the reality that voltage is traveling as a wave over hundreds of kilometers.
Okay, so what is the crucial rule governing all these models? Steady-state voltage regulation. Your absolute North Star as a planning engineer is maintaining that voltage within a strict plus or minus 5% of nominal under peak load. Most electrical codes and utility standards mandate keeping the voltage squarely within a 5 to 10% band, entirely depending on the voltage class. If your models show the voltage sagging below 95% at the receiving end or spiking above 105%, you've got a major engineering problem to solve.
Let's test this with a real-world hazard that catches a lot of people off guard. Imagine you've modeled a long 400 kilovolt transmission line using your shiny new equivalent pi model. Under peak load during the day, your voltage sits perfectly within that 5% limit. But at 2 a.m., when city demand drops off completely, the voltage at the receiving end violently spikes above the limit. What is happening physically on that line, and as the engineer, how do you fix it?
The culprit behind this 2 a.m. spike is something called the Ferranti effect. Here's what's going on. A lightly loaded long line is essentially operating below its surge impedance loading point. Because there is very little load current flowing through the line's inductance, the line starts acting like a giant capacitor. It generates way more reactive power from its shunt capacitance than it consumes, which physically pushes the voltage up at the far end. The standard industry fix? You switch in shunt reactors to absorb that excess reactive power and literally pull the voltage back down to safe levels. You can see exactly how this works in this schematic.
We intentionally insert these shunt reactors, which are basically massive inductors, from the phase conductors to neutral at the ends of the line. This perfectly counters the line's natural capacitance. During those light load nighttime hours, the utility just flips these reactors on. They swallow up that dangerous excess reactive power, keeping our grid totally stable and strictly compliant with our voltage limits. Then, when the morning peak load hits, they just switch them back off.
So think about it. You started this explainer knowing lines were these complex, almost intimidating distributed systems. But look at your toolkit now. You've got 3 concrete, distance-based models to solve them practically. You've got the simple series impedance model for short lines, the nominal-pi model for medium lines, and the hyperbolic equivalent pi model for the long hauls. Plus, you completely understand that golden 5% regulation target, and you know exactly how to combat the sneaky Ferranti effect on lightly loaded lines.
We have successfully modeled the generators, we modeled the transformers, and now we've mathematically tamed the transmission lines themselves. Every individual piece of the grid is ready. So, what happens when we snap all these intricate models together into one massive network diagram and press solve on the entire system? That brings us to the single most important calculation in the entire power industry, power flow analysis. But I'll leave you with this thought. When millions of variables are interacting across an entire continent's grid, are we truly mastering the system or just delicately balancing on a mathematical razor's edge? We'll find out in our next explainer.